So far the only vectors we've seen are constant. Now we want to look at vectors that are actually variables. So the first case we're going to have of this is what we call a vector-valued function. So this is a function that has a scalar value as an input, and then out comes a vector. And it might have 2 or 3 components, depending. So the way we write this situation is we have a vector whose components are individual functions of some variable t. So we're thinking of t as a scalar parameter. F, g, and h are ordinary scalar functions, but together we collect them together and we have a vector-valued function. Now one of the most natural ways of interpreting a vector-valued function is as a space curve. Okay, and what we're talking about here is the situation where we have the position vector, r, varies with t, and it's equal to that vector-valued function. Okay, so that's kind of the compact way of writing it, but what we really mean here is that x is f of t, y is g of t, and z is h of t together. And then if we think of t varying, unless we say otherwise, over minus infinity to infinity, then each value of t designates a point in space. So as t varies, it traces out a curve in space. So one of the more important and famous examples of such a curve is where we have x equals cosine t, y equals sine t, and z equals t. And again, if we don't say otherwise, then t can range over all of the real line. So in order to figure out what this curve might look like without using a computer, first of all, we can notice whenever you see a cosine and a sine, you want to use this basic common identity. So x squared plus y squared is cosine squared plus sine squared, and that equals 1. So we're always looking to use that identity where possible. And so what that tells us is that if you just look at the x and y coordinates alone, they satisfy this equation, x squared plus y squared equals 1, and that's the equation of a circular cylinder. So if we sketch that circular cylinder, where x squared plus y squared equals 1, this isn't the curve, this is just somewhere where the curve has to lie on. All right, so it's just a guide for helping us understand it. Okay, the curve itself then spirals around on this cylinder. And it actually goes on forever in both directions. And we'll use an arrow to show the direction of increasing t. And the reason we use t is to suggest time. So if you imagine t is time, then the position vector shows you the position of an ant crawling along as a function of time. Okay, and this curve is called a helix. So other than a line, it's probably the most important example of a curve in space.